Sorry, I'm a little bit late. Is the aircon on? So how was everything last week? You guys managed to cover all the currents and stuff? So by the way, I'm Cash. I saw some new faces today. Welcome to the lecture. So today we'll cover the layout of our IC design. Have you guys downloaded the lecture notes from LMS? Because mainly we'll be using that. So the labs shall be starting this week, and the lab menus are already up there. It will be in Lab 271. Attendance is mandatory, so you have to go there. And I'll be there to meet you, review what you'd be expecting. Oops, I haven't turned on. Oh, it's on. Yep. I'll be there with you guys. Yep. I'll be there with you guys, trying to go through a whole lab with you, and also I will be when the time comes, I'll be briefing you about the project as well. All right. You're not doing this one? No, all right. You guys are doing IC design, 5503? Okay. So let's jump straight into the lecture. But before that, I need to recall your memory. So get a piece of paper or on your iPad, laptop, whatever. Draw the cross-section area of a PMOS and an NMOS on the same piece of silicon, a P substrate. Oh, let's try this one. We'll draw it on an N substrate silicon. So it'll be slightly different from from last week. So last week we've been drawing the MOSFETs on P substrate. So this time, try to draw it on an N substrate. I'll give you 3 minutes. N substrate, yep. If you forgot what you're supposed to draw, you can flip through your lecture notes. You won't be able to find the exact thing on your lecture notes, but it'll be similar. So just look at the person sitting next to you or near you and check whether you can see anything wrong with their figure. So since it's an N substrate, what kind of MOSFET can we form directly on this piece of substrate? MFET or NMOS or PMOS? PMOS, that's right. So let's start with PMOS. So this is important. It's not just P, but it's a P+, okay? Which means it is heavily doped. And the next thing is your oxide and your poly, okay? Remember, there should be a little bit of overlap here and there. I can accept that if you draw it on the test. I can accept that it is barely touching, but I can't accept that if it is separated. All right, so if it's separated, you are preparing to have your marks deducted. So is that pretty much about the PMOS? Did I miss anything? No? Yep, the bulk. Yeah, that's important. So you should have the N+ here, all right? Well, you can argue that it's hiding somewhere else. It can be far apart from your MOS, but I need to see that in your test, okay? And of course, you need some kind of metal to get your signal outside. And I don't need you to draw the like other metals like vias and other stuff. But for this one, I want to see a little bit of a silicon dioxide here to make sure that your PMOS and your NMOS are kind of separated. All right. So from this one, I'm trying to draw my NMOS. And what well is it? Is it an N well or is it a P well? Yep, it's a P well. So it's not just P, it's a P well. And again, I have your N+, your oxide and your poly, of course, metal, forgive my poor drawing. Is that it? You need the bulk as well, yep. And what is the bulk? What should I put in? P+, yes, that's right. Okay, so that's pretty much about it. So what is layout? Is this a layout drawing? No, this is just a cross-section area, cross-sectional view of your, well, technically it's still a circuit. You only got 2 transistors there, but technically it's still a circuit. But a layout is not a cross-sectional view. Is a top view, okay? So basically, you need to translate this into a top view so that it becomes a layout, all right? So this lecture will be talking how you draw your layout, is any easier ways, and also how you translate your layout back to your circuit, okay? So, layout here. If you've got your lecture notes ready, this is your first ever thing that you'll be drawing on Cadence during the lab. So we'll again be using P substrate. So the N substrate was just for demonstration and exercise. Usually, we don't use N substrate that much. Mainly we use P substrate. So this one, you will have your things ready. Okay, so you can see the blue, these ones, the blue shaded area is basically metal, and you can translate that to this piece of metal here, and you take a cross section here, and it'll be this one. All right. Any questions from the top one to the bottom one? If you guys are having no questions, then I'll skip it. If you guys got a little bit of question, this is pretty straightforward. All good? Are you guys all good? We'll skip it. So this looks pretty natural for you guys to translate this. No worries. So for this circuit, it is an inverter. There is one thing that is kind of different from what you've drew previously, which is the metal connections. So basically, all the silicon related stuff is similar. So all the P+, N+, and poly, they are similar. But the thing, the different part is the metal. So we'll look into it, and yeah. So we'll first look at the ground. So do you remember what is the substrate connected to for an NMOS? P substrate NMOS, should it connect to lowest potential or highest potential? So for this one, this is an NMOS. Should it be connected to VDD or connected to ground? Which one? Yes, NMOS is always connected to ground, so it will never be VDD. And also, if this node is connected to ground, is that a source or drain? NMOS lowest potential is source. Okay, it's a source here. So your gate, your drain, your source. All right. So when you're checking VGS, it's checking the potential difference between your gate and your source. Okay. Similarly, well, I should say conversely, if this is connected to VDD, is this a source or drain? Sorry, source or drain? Yes. No. Sorry. This is I got trapped. This is a source. This is a PMOS. Yep. So this is source. This is drain. Okay. So it's completely opposite for your PMOS and NMOS. This is still your gate. And what does the body? What does the body connect to? Yeah, that's right. VDD. Okay. So ideally, your source, whatever transistor it is, either NMOS or PMOS, ideally your source is always connected to your body, so that you have a minimum potential difference between S and B. So VSB is 0. That will give you the best result. Okay. All right. So let's go back to our layout. So these are our basic stuff. I will remind you on and off, especially for next lecture when we talk about the logics. This is very important. But for today, we are just drawing rectangles. So when we look at the layouts, so basically for a layout, who has done PCB before? Yeah, a few of us. So some of us hasn't done PCB. So this could be unfamiliar to you guys, but it won't be too difficult. So so for those who has done PCBs, you need to slightly tune your mindset, because for PCBs, the vias are always drawing from top, either semi-via to certain kind of metal or all the way through. But for IC designs, our via can be anywhere. So basically, via are the metal used to connect two metal layers. So for example, this is the cross-sectional view, okay? Cross. I got this metal 2. This is metal 1, so our silicon is here, okay? If I need to, so assume I have a N+ here, all right? Assume I need to connect N+ to M1, then I need to draw contact. Contact is usually done by copper. So I have a hole, and then I fill in copper, so that M1 can connect to my metal 1, to my N+. All good? Simple, right? How about M2? If I want to draw, I want to connect M1 to my M2, I need another, well, we don't call it contact, because if we call it contact, then this layer and this layer will be the same. So since they are different in terms of vertical position, we call it V1, okay? And similarly, if you got another layer R, I got my M3, M2, M2, M1, my silicon, M+. So assume M2 is connected to some signal, VA, for example, and I need to, this M3 is connected to VB. And if I want to connect this N+ to VB, then what should I do? So I need to place a contact here, right? I can't do it all the way up because M2 is here, right? So I gotta give a contact here, then the current goes from N+ through the contact to M1, and then I put another, what is that called? Via. Yep, and it's V1. So the name of the via is always associated with the lower metal. Okay, so V1 here, and then I need another via, V3 here. V2. Yep, associated with the lower one. Then the current can flow through from M3 through this one to there. Is that clear? Does it make sense? Right? Yep. So the difficult part of layout is that you have to have both mindset in your head. Okay? So you need to have your cross-section view, because you need to know how it's connected. But also for layout, you draw it on the top view. Okay? So that is the confusing part. But if you can get through this, it won't be too difficult for you to draw a basic layout. But of course, when you talk about optimization, you want to make it as compact as possible, make it as small as possible. That is difficult. And if you have a complex layout, you need to debug it. Accidentally, you put a via here, then it shorts everything. Then you need to debug. That is also difficult. Okay. So for this one, we have 6 masks, which means we have 6 different type of it's not shape, but mask, I would say, when you remember the video first I show you guys, there are masks and you do photolithography, which we'll cover a bit later on. And for those masks are the things that you use to fabricate your CMOS circuit. So basically you make a hole in your mask, you put material in, shine it through the different wavelengths, and then some material will stay there, some material will be washed away, and it forms all these shapes. Okay, we'll cover it later on. But just to give you a brief introduction, you'll see for this layout, this simple layout here on top, you have 6 masks. So you have 6 colors, 6 shading areas that is used to fabricate your inverter. Okay, so 3D structure, you can look through it. You need to know it, but you won't be able to see it in our course. 3D structure is usually used only in very advanced CMOS, but we won't use it in this unit. Representing layout, so be careful. This one, it talks about different colors and stuff. These colors are not the colors that we use in our technology, because depending on technology that you use, they have a default color. Of course, you can change to whatever you like. So basically, you can have your own profile, change your colors to fit your preference. But usually, people will just use the default ones. Okay. And when you go to the lab, when you're doing the layout labs, I'll brief you again what we have in our lab. Okay. So transistor. All right. Remember when I say on a piece of silicon, on a layout, if you have a piece of silicon, and so assume all the white area is your substrate, okay? So assume this is a P substrate, okay? And then you have a green, we call it active area, which means it's heavily doped, but you haven't specified whether it's an N plus or P plus. So you will usually specify it by adding another box before outside your active, saying, okay, this is my N plus, okay? And then your active area, effective active area is this part, the green part, okay? So your blue box, basically you just specify what it is going to be in your active. So you can make it as large as you want. It doesn't change anything in this situation. So you have an N plus active, and if you look at the cross-section area, you have your P sub, and then you have this, apparently, it should be your N plus, right? Okay, so you have a big block of N plus. And then you put in a piece, oops, I should use another color. Apparently, you put in another piece of polysilicon. All right, then straight away you'll think, okay, this is what I made. And is this a transistor in your cross-section area? No, it's not, because you only got one piece of N plus and a piece of poly sitting on top, right? But the layout view will automatically translate something for you. So as soon as you do it this way, it will break your N plus, oops, and it becomes like this, okay? And then this is also N plus. So now, is this a transistor? No, it's not. You're missing an oxide, right? But Cadence will do it for you as well. So it will also give you this, and then include this for free. All right, now it becomes a transistor. Okay. So whenever you have this one, then you know this is transistor. To simplify it, when you see a poly crossing an active area, then it's very likely to be a transistor. All right. Okay. And this is a N plus. And if you want to make a PMOS, what should you do? What extra things you need for PMOS? Yeah, well, so I'll use the same color for same thing. So this is your MOS. So you will have this active area. You will still have a poly, but this time, so the blue thing represents N plus, right? So I will use a yellow box. Now I specify this to be P plus. Okay, and on top of P plus, you need another one. Purple. You need this ML. Okay, then this is your PMOS. So when you see, oh, it's not quite clear. This is your P plus. Okay, so whenever you see the top one, a poly crossing active without an ML, most likely it's going to be MOS. If you see an ML inside the ML, you have a poly crossing a P plus area, then it's quite likely it will be a PMOS. Okay, so it depends on other factors as well, but they could be complicated. That's why I say most likely. So you got to double check. Is that clear? Oh, good. So these are just examples. We won't be using these colors. But one thing I can tell you, you can't make things as large as you like and as small as you like. There are certain rules that you have to follow. They are called the design rules. So for example, when you have a poly, you can't draw something like this. Oops. Technically, this is still a transistor, right? It's not really crossing, but you know the top part and the bottom part sticking out is pretty much useless. It's not effective, right? So technically, this one is still kind of a transistor, but in the actual layout view, you can't draw something like that because there are certain design rules that specify how much you need to extend it and how much you need to extend it, okay? And also simple things like You can't put two active area too close to each other. There are rules that you need to make a certain distance, because in actual fabrication, you need to leave it a bit of margin. Otherwise, you think it's close, but not touching. But after fabrication, you realize it's short. So that's why the rules are helping us to make sure our design will be fabricated as what we want. Okay, but all these rules make our design a bit more larger instead of more compact. So there are pros and cons. Some people, when they are very aggressive, they try to push over the boundary. For some foundries, that could happen. So, for example, if the design rule between I got two pieces of metal, say I got my M1 here, I got my other M1 here, and the design rule says the minimum should be I don't know, for example, 0.1 mil. So just for example, say the rule says it's 0.1 micrometers. But then the thing is, if I can make it 0.8 micrometers, then my performance could be a lot better. Then you can file in and ask the foundry, say, oh, I want to push it to the boundary. Will it be possible? They might say, well, for some rules, they will let you do that, but for some rules, they won't. Okay. So basically, it affects the yield. So if you make it 0.1 micrometers, the chance of touching these two metals, the chance for these two metals touching could be like 0.01%. But if you make it 0.8 mil, the chance of touching could be 20%. Then your yield is dropped a lot. So it depends on the foundry whether they will allow you to do that. But for our course, again, you don't have to worry about it. Just follow the rules, okay? Don't push my boundary. All right. This is something engineers like, reverse engineers. So basically what it means is that you look at other people's product and then you try to figure out what they're doing. All right. And one thing for layout is that you try to reverse engineering, which means from a layout. So basically this layout is something that probably you can buy off from, I don't know, from RS or from some other companies that they make this, and then you open their package and then you scan it with X-rays and stuff. You find that, okay, this is their layout. And what exactly the circuit is, I don't know. And then you're trying to figure out what is the circuit behind this one. So how do you do that? Any ideas? Yep. First thing is that you can identify the well. Well, first thing is that you identify the substrate, and then you identify the well. What's the point of identifying the substrate and the well? Yeah, but why do you have to do that? That is very important. First, you need to identify what kind of MOSFET it is. So if you see this figure, you can see something on top, something down the bottom. They could be similar MOS, but is top one PMOS or NMOS? Is the bottom one NMOS? I guess so. How can you be certain that the bottom one is NMOS, the top one is PMOS? Well, when we do our exams and tests, we always put PMOS on top and NMOS down the bottom. But this is a real thing. This is a real problem. You can just reorient it, and then you'll find that it could be difficult, or you put it on the side, you don't know which one is which. So identifying the substrate first. So if it is a P substrate, this is something that we are familiar with, that's good. And then we identify where the well is. So for this one, I would say this is our N well, and this is our P substrate, okay? So on top of our P substrate, there is a green active area here. What is it? Is it N plus or P plus? Yep, usually it's N plus. Well, this is a real reverse engineering problem. In test, I'll tell you what is what, yeah? And these are P plus. So straight away, we know that these are PMOS and these are NMOS, right? So how many NMOS and how many PMOS do you have? Two each. That's right. How do you know? Yep, there are two polys. That is very important. Well, not just two poly, but two poly crossing the active area, okay? So whenever you have a active area, poly crossing it, that is your effective MOSFET, okay? I'll draw it with another color. So whenever you have this one and this one crossing, your effective MOSFET is identified here, okay? So all the main stuff happens, like saturation mode, linear mode, all happens in the channel, right? So this is your active MOSFET. So here we have two polys. So let's look at the PMOS. We have two polys crossing the active area. So we have two PMOS. Same for your NMOS. Two polys crossing your NMOS, crossing your active area, two NMOS. Simple enough. So what I'll do is that after identify I have two each, I will draw something like this. That is my NMOS. Well, I'll just cross this. Don't forget the circle for your PMOS, okay? So I'll have something similar to my right-hand side, right? Let's start with the NMOS, because NMOS is usually easier and it's less complicated. So we have our very left-hand node, which is this one here, having this via, and it's connected to my metal, right? So I will have this one connected to, I say this is my VA, this is VA. Clear? And then in the middle node, this node is connected to nothing, so I leave it floating. And for this node here, it's connected to somewhere, this node, the node between two PMOS. So I just draw a node connected to here, okay? And for my PMOS, the left-hand node is connected to the metal. I say VB, so I have a VB here, connected. This one we have already done, the middle one. The right-hand side is also connected to VB, all right? So it'll be something like this. Simple enough. But if you give me something like this in your test, definitely I'll only give you half of the mark because you need to tidy it up. How do you tidy it up? Because you need to translate it so that it's easy to read. Just like assuming I'm giving you a test. If I say, this is the circuit, tell me what the function is. Well, I can do that, but you can't. Okay. So usually what we do is that all the MOSFETs, we draw it in that direction or that direction. Okay. We have this PA and PP. PA and PP are in series or in parallel? PA and PP, are they in parallel? Parallel. How do you know? Yep. So basically the source are connected and the drains are connected while the gates are not. Well, if the gates are connected as well, then it's basically one PMOS, just one bigger PMOS. But since their drains are connected, their source are connected, and their gates are different. So, oh, sorry, I haven't finished with my thing. Because the gates are floating, right? You need to connect the gates as well. It is connected through this poly here. So this one will connect to here. This one will connect to here. Okay? Then it's finished. But finish as in not yet finished, but like conceptually. So for this one, I will say this is A, this is B. So I have A, B. Okay? And then I will have this node connected, which means these are connected in some sense. Okay? So this is VB, and this node here connects your PMOS and NMOS. Give a name, I say F. Okay? So this is F, and it connects to my NMOS. Well, at this point, this is F, and goes to the first NMOS, NB, and this gate here connects to B, right? So I know this connects to B, right? And goes through a series, and it connects to A, and connects to BA. All right? So in your tests, feel free to leave all your gates floating with label. What I mean is that you have a label, just label your gate. You don't have to connect them. So you don't have to draw something like this. And for me, it just make it messy. So feel free to do it like this. Okay? It's clear. I know what you're doing. And supposedly you can only do this when you know what you're doing. Is there any questions? Is it too simple? Or is it too hard? I need some feedbacks. It's good? Okay. In that case, don't look at your lecture notes. Everyone try to do this one. This one here is quite similar. So remember what you do. First, identify your substrate. Second, identify your wells so that you can find the PMOS and NMOS and the number of it. And then draw something like this figure. And finally, do all the connections. Okay? All right. I'll give you 5 minutes. It's not a quiz, so no point to look at your lecture notes. I need to know what you don't understand. And in order to know what you don't understand, the only way is that you try to do your problem and you find out you can't do it, and let me know what your problems are. So just to let you know, this poly is connected, okay? And also this is connected. Oh, you know what I mean? Okay. So one question is that how do I identify the substrate? I think it's a very good question. Apparently in the question, I didn't tell you what substrate it is. So if I didn't tell you, you will assume it's a P substrate. So all the background color stuff is your P. So for this example, all the white stuff is your content. And again, if I didn't specify, then you assume the well, it will be an N well. Another very good question. Do you have to draw the body? What do you think? Well, in terms of digital circuits, you don't need to draw the body. Because the body for PMOS, the body is always connected to VDD, and for NMOS, the body is always connected to ground. Okay, so in a digital circuit, you don't have to draw the body. Okay, so of course, when you're doing a lab project, in the simulator itself, you need to specify which potential it connects to. But in terms of these endpoints, you don't draw the body. It won't be wrong, just that the body you draw usually only sticking memory. So it's not necessary. Okay, so I think most of us got most of it. So just a little bit of reminder. So in your very final answer, the one that you're going to submit, it will be your transistor will be like this or this. Okay, quite unlikely you'll get full mark when you draw a transistor like this. Okay, well, to be honest, I'm not going to deduct your mark too much if you draw this, but it is very confusing if you have a horizontal transistor. That's just a convention. Okay, yep. I can't actually deduct your mark if you have a very clear. So, for example, you can draw this like the whole thing horizontally. I can't say you're wrong, but conventionally, we'll draw something in vertical direction. Is that clear? Okay, so this is similar to what we did. I'll just go quickly. So first is that you identify there are two PMOS and two NMOS. So the top part is your PMOS, the bottom part is your NMOS. If you don't understand, let me know. So I'll have one PMOS, two PMOS, one NMOS, two NMOS. Okay? And then for your left-hand node is connected to your right-hand node, connected to some voltage. All right? So I say Vs. And then the middle node is connected to your top part, left-hand node. This node is not connected to anything. This node is connected to another voltage. I call it Vd. All right? And this is your A, this is your A, so they are connected. This is your B, this is your B, so they are connected. All right? And just to draw it nicely, then you have, and this is your F. So is that correct? Is that correct? Anyone think I'm wrong? Yep. This one? Okay. This one? Oh, it's the same. So your question is whether I can draw it like this, or I should draw it like, or I should draw it like this, right? Basically, the two are the same. Yeah. So other than that, oh, by the way, if you're drawing like this, well, actually, all the nodes, I suppose you to draw a big dot showing that they're connected. All right? Because sometimes when you have cross, I don't know whether you're meant to connect it or not. So is that correct? Anything wrong? Maybe I put it A, B, B, D. This is F. This is Vs. Okay? Everyone thinks I'm correct. I actually did a mistake here. And can anyone tell? So yes. Yeah, that's right. So this is very important because we are often thinking that, okay, so if it is a parallel, I do it this way. If it is a series, I put it this way. And then whatever the gates are, and then I can just assign them randomly. But in terms of reverse engineering, you have to do an exact translation. So if this is the case, my VD first passes the A transistor, then goes to the B transistor, and then goes F. But in your layout, my VD actually goes through B transistor first, and then to my A transistor, and goes to F. So this part has to be a BA. Okay? But for NMOS, because they are parallel, it doesn't matter whether it's an A or AB or BA. It doesn't matter because they are parallel. You can literally swap them around. Okay? So if I did what I did in my cadence layout, it will report there is an error. So when you are doing your project and labs, you need to be super careful because you'll be thinking like, okay, I have two transistors in series, then why is it reporting an error? So very often, the reason is that you've mixed up the inputs. Yes? Oh, you mean this and that? So yes, just like it says this is the output, but the thing is in the actual diagram, it didn't say anything about VDD, ground, output, all those things. So these conventions are just a little bit of extra information. Well, in the actual test, it should be given, all right? If I didn't give you anything, make sure you draw something like this on your layout, and then in the schematic, you use the same convention. Yep. All good. I'll give you, do you guys need a break? Some needs a break, some don't. 5 minutes. Give you a 5 minutes break. And if you have nothing better to do, just think through what you've learned. Ask me if you have any questions. Yep. Can you guys hear me? Yep. All right. So these are the two input NAND gates and two input NOR gates are just simple gates. Very often you have custom design circuits like this. So basically the principle is still the same. First thing is to identify where your PMOS and NMOS are, and then you try to do the connections. So I should let you guys do this problem during your break. Try to do this, but I think there's something wrong with the printings, so I need to clarify a bit. So this one is connected, and this one is connected, and also this box is connected here, and it's a bit dodgy, sorry about that. Okay, it looks more right. Okay, so see, is that clear? Yes, the yellow thing is NWell. So this is your ML. Ah, okay. Okay. Yep. So let me. Also, this is C. Okay, your third poly is C, and I would say this is your VDD. This is your ground, and this is not A, but this one is your F. Do I miss anything? No. Feel free to name all the internal nodes if you want, but if you don't want to name the internal nodes, you don't have to. Okay, so try to do this one and see if it is as easy as the previous ones, or do you think it's slightly harder? Let me know what you think. I think you guys can finish it in 3 minutes. You guys need more time? Okay, sure. Who thinks your neighbor needs a bit more time? No one? Okay, so, all right, let's come back to here. Is that difficult? Yeah, a bit more complicated than the previous one, right? Why is that? Because there are more connections, there are more transistors. But if you go back to the principle, they should be similar in some sense, of course. The more complicated it is, the more likely that we'll make mistakes, but it's okay. So let's all go through it. First question, how many PMOS and how many NMOS do you have? Quick answer. 5 each. Yeah. So, oh, by the way, when I saw I saw you guys can kind of divide into 2 groups. One group wants to do these kind of schematics straight away from the layout. Some students tend to do this first and then do this one. I'm fine with both. Definitely, you need to give this kind of style at the end. If you feel like you're quite likely to make mistakes, so I want to draw this one first, it's pretty fine. So if you draw this straight away, if you have some kind of mistakes in between, I won't be able to give you any marks. But if you've got this correct, and then when you translate this into here, if you got some kind of correct answers, then I can still give you some marks. But definitely do this really quick, okay? So it depends on your role. So yeah, I've heard that we have 5 PMOS, 5 NMOS, okay? So 2, 3, 4, 5 PMOS, 2, and then 5 NMOS. So as far as I know, it's A, B, C, D, A, B, C, D, E. Correct? Okay, so you got some marks already. And then we can identify the ground and the VDD easily, right? So whenever we have a ground, you don't have to use different colors if you want. I use different colors just for the purpose of having a bit more clear illustrations. Okay, so I have my VDD and ground. Let's do ground first. In this node, the left-hand side of A is connected to ground, right? And then the next one is the right-hand side of C is connected to ground. And also the right-hand side of E is connected to ground. You guys got that as well? And then for VDD, there's only one connection between VDD and this one, which is A. Okay? So we've done half already. And then we actually found out some of the PMOS are connected with their neighbors and some are disconnected. Okay? That's why for these ones, I left a gap here for my P1 and N. So we'll see which one is joined, which one is not. So if we look at ABC of both PMOS and NMOS, the green area, which is the active area, they are all connected without a gap. So we know that A and B, B and C are connected. Same for my NMOS. A and B, B and C are connected. But C and D are not. They're disconnected, right? You can see, oh, I'm not sure whether my voice can be kept. C and D are disconnected on both NMOS and PMOS, so we just leave it there, do nothing, okay? And then my D and E, they're connected, so I connect them. All right, so by now all my silicon and poly should be done, and we are just left with some kind of internal node, and let's do it one by one. From NMOS, we have our right-hand side of A here, connected to F, right? And then the left-hand side of D is connected to F as well. And that's it. And for my PMOS, F is only connected to one node, which is
somewhere between D and E. All good. And then I have some internal nodes, which is left-hand side of D and right-hand side of E. They are connected, and then it connects to the node between B and C, right? And then for C, right-hand side of C is connected to the node between A and B. All right, I think that should be about it. Did I miss any nodes? Let's double check. So how I do my double checking is just to go through from top to left, top to bottom, left to right. So I'll check. I'm not tall enough. I'll check this node first. So start from here, go through here, and then I do here, go through there. Okay. So A, yep, left-hand side of A is connected to VDD. That's good. Right-hand side of A is connected to this internal node. Okay. And then B, right-hand side of B is connected to another internal node. So if you want, as I said, you can name the internal nodes. Okay. So maybe you can name it as P1, this as P2. So you can see A is connected to P1, B is connected to P2, and then the C is connected to P1, right? And it's connected, that's good. And then D, P2, that's good. This one connects to F, that's good. This one, final one connects to P2, that's good. Okay? And do a similar checkup. I don't assume I have any errors. If you find out, let me know. So if I have something like this, am I done? Can you submit this to your examiner? No, never submit some kind of these figures to me, because definitely it's not hard for you to translate it back to the standard symbol conventions. Okay, so in a standard convention, straight away you can translate the right hand figure to your left hand side. Any problems for you to translate that? Is any difficult condition or difficulties for you to translate your right hand side figure to your left hand side, or is it simple? If you guys think it's simple, then I'm not going to cover it. All good? Okay. So go home, try to do a 1 or 2 exercise. If you find any problems, let me know. Okay? All right. Here's just another problem. Ooh, okay. Here's just another problem. Do you guys want to do it now? Because I think, yeah, we can do it quickly. 5 minutes maximum. Try to do this. Okay? Actually, I want you guys to do a complete translation from this layout to a schematic. I'll give you a bit more time. So again, pay attention to the node. It's not A, B, C, D, E anymore. And also this one here is just a piece of metal. And for simplicity, I'll name these internal nodes as well. So this is P1, this is P2, this is F, this is VDD, this is G and D. Okay? Just a little bit of note. So in the PMOS, you saw there are 2 contacts, right? You can afford, because the PMOS are wider, not longer. Remember, it's wider for your PMOS, so you can have the space for 2 contacts. So the difference between 1 contact and 2 contacts, logically, is the same. Just that its performance will be different. Okay. So as long as you know they are connected, it's fine. But for your MOS, because it's not wide enough, so you can only afford 1 contact. All right. That's just a little bit of side notes. Okay, looks like most of us got that without too much difficulties. So
we'll just quickly cover that. So this time I'm not gonna draw it this way. I'll just draw it straight away. So one thing we can notice is that, again, we have 5 PMOS, 5 NMOS, and they are all connected. I mean, the active area is all connected, not like this one. So this one got a little bit of a gap here, but this one, they're all connected. So in terms of size, it's more compact. So that's just my preference. When I'm translating the layout to a schematic, if it's simple layout like this, I'll start with the ground. You can start with VDD if you want, doesn't really matter. So I start with the ground, and I see there are 2 connections here. So does it mean it connects to 2 transistors? Look at your answer. Does it connect to 2 or 3 transistors? 3, because, well, for this one it's 1 transistor, but for this one, it actually connects to 2 transistors, okay? So I will have 3 transistors, and they are all NMOS. The first one is C, the second one is A, and then E, okay? And then for my A, well, you just pick one basically. Then for my A, I'll go from here. So it goes to E and then go to D. There's nothing in the internal node between D and E, and then it goes back to A. All right. And then in terms of C and B, there's nothing here. This is B, and then this node B connects to this one, connects to this one here, right? So this one is B and A and D. All right. So that's your NMOS, and that is your F. Okay. So if you think this is too quick, feel free to do it this way. So again, this is safer. Just I'm lazy, so I do it this way. So then I still build upwards and start from F. Does F connected to 2 PMOS or 1? It only has 1 node. 2 PMOS, yep. So it's E and D. So I'll use another color. It connects to E and D, okay? And then they are in parallel and share this node P2. So I have P2. So if in your test, I've given you the name of the internal node, the label, you have to put it down in your schematic. Okay, don't forget that. And P2 is actually connected to nothing, right? Or is it connected to something? Connect to what? Yes, P2 connects to one side of A. So we have this one, A, and then A is connected to P1, P1, and I don't have much space. And you can see that C and B in parallel and connected to VDD. So just to be quick, this is the lazy way of drawing. Not really recommended, but if you're running out of time, then I can't mark you wrong. Yes. This one? Yep. It's given. Yep. That's why even if you don't know, make sure you put down all the internal nodes. Then you will get full mark. And very often people ask me, how do I know this is the output? Well, you actually know about it in the next lecture, but usually whenever PMOS and NMOS join together, that is your output. Okay. That only applies for CMOS circuits. Yep. It doesn't apply for everything. Okay. So sorry, I have to make that small because I want to show you this and that. Look at these 2. Do they have the same function or do they have different function? Can you see? Oh, it's super small. Sorry about that. What should I do? I can't copy anyway. That's a bit dodgy, but hopefully, well, if you can't see it, read your lecture notes. So what my point is, if you look at the top schematic and the bottom schematic, they are slightly different. And who can tell me what's the difference? The top and the bottom schematic. Yep. So especially for your A PMOS here, this one takes parallel, doesn't really matter where to put it, and also yeah. So main difference is your A and BC, right? But in terms of functionality, are they the same? What's the difference? So assume F is the output. Yeah. Yeah. So you'll learn more tomorrow. But in terms of functionality, these 2 circuits are the same. Okay. So when I say functionality, means the Boolean output. Yeah. So whatever combination, A, B, C, D, E, whatever combination, if you put it on the top circuit, and then you'll get some kind of output F. And if you put the same combination into your second circuit, the bottom one, you'll have the same F. So that is what I mean by the same functionality. But just by rearranging your A and BC, then you'll have a much smaller circuit. So in terms of output, if you look at the top output and look at the bottom output, the scale is pretty much the same. You will find that it is much smaller. Do you know why? The bottom one is smaller. Well, actually, yeah. So even for this one, don't worry. The reason for the top one and the bottom one, they have a difference in terms of size, mainly because of the gap here. So for this one, you need to leave a large gap, and also you need to draw another diffusion for the MOSFETs. Just by rearranging it, you'll be able to have a shared diffusion, no gaps, so you'll have a smaller layout. And for all of these, not today, you'll learn later. Well, this is some kind of optimization. You'll make sure you are master of this so that you can do well in your project. All right. So
reverse engineering. Any questions? If not, I'll go to the next part. So perfect news. For these ones, you just have to read through your lecture notes. It could be asked in your tests, but if you don't understand, let me know. So they are, again, physics. Design rules. So as I said before, there are certain rules that you have to obey when you're drawing your layouts. Some kind of space requirements, some kind of extension requirements. And the good news for this one is that lambda-based rules does not apply anymore. So you don't have to remember all these numbers. So basically, every single time, you just have to check your rules in your design. Unfortunately, for our lab, the design rule itself cannot be provided to students due to NDA sign. So what you can do is that I'll explain again in the lab that you can have another way to find out what the design rules are. Okay, so it will be embedded in the technology itself. So don't worry about these 0.5 micron super old technology. Don't worry about it. Substrate biasing. Yep, that's important. As we said before, don't forget to bias your substrate. So substrate is your body. And if you don't bias it, basically your transistors are floating. And when you are biasing your substrate, so assume this is your transistor. You have multiple contacts, okay? And this is another transistor. You only have one contact. Will that make a difference? From the perspective of performance. So in terms, sorry? Noise, yes, it depends on how you define noise. But definitely there will be a performance difference because I asked you about this. So if you look at the cross-sectional area here this time, okay? So you have metal, M1, you have substrate. Actually, not substrate, your M+, okay? If you have 3 contacts, it'll be like this. And if you only have 1 contact, it'll be like this, okay? Each contact will have their own resistance. So it will be small, but still a fair amount of resistance, okay? So in terms of this one, what kind of resistance you have? You have 3 resistance in parallel, so it'll be R divided by 3. But for this one, if you only have 1 contact, then it'll be R. So the resistance for this one is 3 times smaller than this one here. Therefore, the more the better in this sense, okay? Only in this sense, in terms of resistance. Why do I care about resistance? Because especially for your drain and source, there will be current going in, going out. If you have an I, so we all know V equals to IR. If your R is 3 times bigger, then your voltage drop will be 3 times larger, okay? Yeah, so you want to minimize this R provided by your contacts. Same for your substrate. Assume you have an NMOS transistor, ground, okay? You connect it to this 1.2 volt. Well, I'm not going to calculate the current anymore, but in your body. Remember I talked about your V threshold, VT, actually depends on your body biasing. If your VSB is large, then there could be a problem to increase your VT. So you have a slower transistor. So if your this one and this one got a little bit of voltage drop, that will cause you a higher VT, which is not desirable. And also for your body as well. So if you lay out your transistor, you assume you have your body here. So it's close enough and you put as many contacts as possible. I don't know how many you can put in, just to put a ring surrounding your whole thing, okay? That's the best you can do. So you will have your VB very close to 0 volt, very close to ground because you put a lot of contacts in. But if you put your transistor here, and in order to save space, I put a lot of circuits here and there. And I just put a little 1 contact for your body. It can still pass your design rule. Well, the design rule specifies, say, there will be 1 contact, at least 1 contact, to connect your body to ground within a range of 20 micrometers. So within these 20 micrometers, you can put a lot of stuff, but you just put 1 body contact there. Essentially, you are putting a huge resistance at your body for this transistor here, and this is connected to some other source and drain, okay? So this huge resistance will also affect the analog performance, speed, current, and other stuff, okay? So if you're just looking at the functionality of the circuit, it's okay, completely okay to just put 1 small contact down there. But that's why for if you're doing analog IC design, you will try to put as much contact as possible. One is to surround the transistor so that noise cannot couple in, but also you want to minimize the voltage difference between your source and bulk. Okay, so interconnect, well, here it talks about the IR drop. So if you have 2 transistors in parallel, this is VA, and you assume your this is the source of A, this is V source of B, you assume VSA equals to VSB, right? Because they are connected, but actually it's not. Just like your PCB, there will be some kind of resistance on your interconnect wires and stuff. So if you want to make it the same, you need to lay it out that way, okay? To make sure the distance travel from point A to this distance, A to C equals to B to C, okay? All right, well, if you are having this sense, that will also do. You share the diffusion because they are essentially 1 node. So you share the diffusion, that's even better. All right, So these are just conceptual stuff that you need to keep it in mind as you design. Yeah. So stick diagram is another thing. We still got a little bit of time. Yeah, we'll cover the stick diagram as well. So stick diagram is one way that you can draw a quick layout in terms of sketches, and also when you have some kind of concept, you see whether this works. So stick diagram basically just translate all your layouts into lines. So you will usually use different colors for this one. So again, it's not necessary to bring different color pens to your test, but it would be good if you could, because when you're drawing stick diagrams, then you can show it clearly what kind of signals you're connecting to. So usually you'll just use one line for your active area, one line for your, so that's your P, that's your N, and then you use another color for your poly. So right now, I know that I got 2 PMOS and 2 NMOS here, all right? And then you just draw all the interconnections. Make sure you put a cross there if they are connected, all right? And that's your ground, that's your VDD. I don't know what function it is, but it is conceptually, it is how it works. So you don't have to draw the complete layout like all the rectangles and stuff and shade it. So this is a lot simpler. And in your test, expect to draw some stick diagrams. In your final project report, expect to draw me some final stick diagrams as well. It should be easy, right? Yeah, make sure you got the cross. So if you have here, right, I would assume this is disconnected, all right, because you don't have a cross. Okay, yeah, checking layout, that is the final part of your layout. So once you finish your layout, you'll do 2 checks. One is called DRC. DRC is to check whether your layout matches the design rule. If there are space requirements that doesn't match, violations and stuff, your DRC will tell you there's an error, you have to fix it, okay? So in our technology that we used, we will have 2 DRCs. One is to check the silicon part, one is to check the metal part. They just make it separate. And then after your DRC, make sure you clear all the violations, then it'll be LBS, which is to check whether your layout matches your schematic. Because as you design it, you'll first design it in your schematic, and then after all the performance and all the simulations are done, then you draw your layout. And finally, you check whether your layout matches your schematic. If they're all good, then you're good to go. Post-layout simulation is that after you draw your layout, you ask the computer to translate your layout back to a schematic with all the parasitic capacitance, resistance, and stuff in there, and then do another extensive simulation. And usually, if you didn't leave any margin as you simulate, usually there will be some kind of performance degrade and errors in your post-layout simulation. All right, photolithography, just go home with your lecture notes. All good. Thanks for coming. I'll see you tomorrow in the maths lecture. And if you have any questions, feel free to ask me tomorrow or drop me an email. Thank you.